Now that we know about the basics of symmetric encryption, let's talk about an important concept called a block cipher. In a block cipher, basically, there are two algorithms, again, as usual, algorithm E and D, and these algorithms operate on fixed size blocks of inputs at a time. So here the algorithms operate on n bits of block at a time. The input is n bits, and the output is n bits as well. And of course, both the encryption and decryption algorithm are given the same key, which is why this is called symmetric encryption. Now, two canonical examples of block ciphers are triple DES, which basically has a block size of 64 bits. So triple DES will take as input 64 bits of plaintext and output 64 bits of output. And similarly, decryption would take 64 bits of output and output 64 bits of input. And the key size for triple DES is 168 bits. Triple DES is a relatively old algorithm and is somewhat slow now. A more modern block cipher is called AES, the Advanced Encryption Standard. The Advanced Encryption Standard actually has a 128-bit block, and it uses variable size keys, 128, 192, or 256, depending on your security requirements. Now, why these parameters are set the way they are for AES is something that we're going to talk about in the crypto course. I don't have time to describe that here, and we're just going to work with these parameters as a given. But there are very good reasons why you want the block size to be 128 bits and why you want the keys to be of these particular three sizes. So how do we build a block cipher? They're all kind of built using the same paradigm that works as follows. The key K is given as input, and the first thing the block cipher does is it takes the key K and kind of expands it into a number of keys called round keys. In some sense, what's happening here is that we run the key through a very weak pseudo-random generator to kind of generate these round keys K1 to Kn. Now, the core of the block cipher is what's called a round function. The round function basically takes the appropriate round key and the output of the previous round and produces the output for the next round. So in particular, the way the block cipher would work, it would start with an input plaintext M, and again, this would be a fixed size input, say n bits for some fixed n, and then it would apply a round function using key K1, and then the first round value would come out. Then it would apply the second round key K2, and the third round value would come out, and so on and so forth until we reach the last round, and then the ciphertext is produced. So just to give you examples, for triple DES, for example, the number of rounds is 48. For AES with 128-bit keys, the number of rounds is 10. In fact, for AES with larger keys, the number of rounds is also larger. Okay, so this shows you at a very high level how block ciphers are built. But of course, the smarts in building a block cipher is in designing the round functions and in designing this key expansion process. So as we said, the core of a block cipher are the round functions, and how the round functions work in particular is not that important for our discussion here. I'll just give you one example. For example, in triple DES, the round function is repeated, as we said, 48 times, and it has this particular structure. Remember, the block size is 64 bits. So in each round, you take your 64 bits, you break them up into a left part and a right part. And then what happens is, we're going to have 64 bits also output, again, a left side and a right side. And what happens is the right side essentially is just output as is, well, on the left, and then the right side also gets passed through a certain function. This is the function that actually uses the round key. So that's a function of the round key and the value on the right. And the output of that is XORed with the left part, and then the result is produced on the right side. Okay? This is basically just writing in pictures what's written here as a formula. So this is the example of what the round function in DES is, in triple DES is, and this round function has been repeated 48 times to actually generate the output of the actual triple DES block cipher using a particular key. As we said, in AES, the mixing is done 10 times. Now, the thing that I want you to remember, even though I explained at a very high level how block ciphers are built, I want to emphasize that it's very difficult to build secure block ciphers. And in particular, you have to resist very sophisticated attacks, which I don't have time to explain here. But the point is that designing this key expansion step and designing the round functions is actually fairly difficult. And it takes many years of experience and many years of review. And that's not something you should do yourself. I would recommend that in any system where you need to use a block cipher, you would basically use one of these two, preferably AES, which is the modern standard for a block cipher. So let me ask you just a quick puzzle just to make sure we're all on the same page. Here is the DES round function, as I said. So on input XY, the output is going to be VW, and I wrote in as a formula what VW is as a function of XY. Now, This is we're computing the function in the forward direction. To decrypt, of course, we're going to compute the function in the reverse direction. And the question is, what is the reverse function? So I hope everybody said that this is the reverse of the round function. And you can, again, very easily see that basically v gets mapped. Here, I'll change colors here. V gets mapped to the y input. So this part is simply v. And then w, what do we do with w? Well, we take v and we push it through this function f, and then we XOR the result with w, and the final value is output on the left. And that's exactly what's written here. Okay, so that's why this is how you would decrypt the des function. It's very interesting, by the way, that the reverse function looks very similar to the forward function. Okay, so rather than explain exactly how AES and triple des work, it's much better that I actually explain to you how to think about them abstractly. And the abstract concept of these block ciphers is something called a pseudo-random function and a pseudo-random permutation. And it's very healthy to think of these block ciphers in terms of these PRFs and PRPs, pseudo-random functions and pseudo-random permutations. So let me explain what these things are. So a pseudo-random function is basically a function that has two inputs. So it takes a key and a plaintext, and then it outputs some outputs, which you might want to call ciphertext, but I refer to it as simple output. And the point is that this algorithm that computes the function f is an efficient. So given a key and an input, there's an efficient way to actually produce the output y that is the output of the function. Now, a pseudo-random permutation is very similar. So I'll denote a pseudo-random permutation by e. It's very similar, but right, again, it's a function that takes as input a key and a plaintext, and it outputs some output. And again, there's an efficient algorithm to evaluate it. However, once you fix the key, the function is one-to-one. In other words, for every output x, there's only one input x that maps to that output. What that means is that there's actually a way to invert. In principle, there exists a way that given the output of the function, we can actually invert it and get the input x that was given to the function. So in a PRP, there's a requirement, there's in fact an efficient algorithm for inverting. That's what's sometimes called a decryption algorithm that takes the key and the output of E and produces the input. In other words, let me quickly write that as an equation. If I encrypt a value x and then I decrypt it using the same k, I should get the original x back. Okay, so, and again, remember these x's belong to these spaces that, fixed size blocks and so on. And again, I want to emphasize that a pseudo-random function need not necessarily be one-to-one. In other words, even though the key might be fixed, there might be two possible x's that map to the same y. Okay, so PRF is not something that can be inverted necessarily, whereas a PRP necessarily can be inverted and in fact can be inverted efficiently. So of course a block cipher is simply a PRP because, well, it's made up of these two algorithms, E and D, that do what you expect. Okay, so a block cipher really is a PRP. So now we understand syntactically what PRFs and PRPs are. Let's define what the security property is. So we say that a pseudo-random function is secure if basically, again, once the key is fixed, once the key is chosen at random and fixed, the resulting function is indistinguishable from a random function from the set x to the set y. Okay, so we cannot distinguish the function f from a random function. And let me explain what that means. Here we have a simple cartoon down here to explain what it means to be secure. Well, so imagine you have an adversary here, and the adversary is interacting with a particular challenger. The challenger does one of two things. Either he chooses a random key for the PRF, or he chooses a truly random function from the set x to the set y. Now, maybe I didn't mention it, but the set x and y are finite, so the set of all possible functions from the set x to the set y is also finite. And what is little f here is literally a random choice, a uniform choice from this finite set of functions from the set x to the set y. Okay, so what happens is this challenger here chooses either a random key for the PRF, or he chooses a truly random function. Now, what does the adversary get to do? The adversary basically gets to submit queries. So he gets to choose an x in the input space, submit the query, and then what he gets back is either the evaluation of f of x or the evaluation of the pseudo-random function. And he's allowed to do this again and again and again. Of course, every time the challenger is going to be consistently answering with the little f or consistently answering with the PRF. Okay? And the question is, can the adversary tell, is he interacting with a truly random function, or is he interacting with one of these pseudo-random functions? And if he can't tell which one he's interacting with, then we say that the pseudorandom function is secure. And it's exactly the same thing with the pseudorandom permutation. Basically, we allow the adversary to interact, with either the permutation using a random key or with a truly random permutation. And if the adversary can't decide which he's interacting with, then we say that the PRP is secure. Now, I just want to be clear, when I say a random permutation here, what I mean is actually a random one-to-one function. So it's a random one-to-one function from x to x. And the adversary can't distinguish a random such function from a random instance of the PRP. Okay, so just a simple fact for you. In fact, it turns out that a PRP is strictly stronger than a PRF. And in fact, any secure PRP is also a secure PRF. So that means that things like AES and triple DES, we're also going to think about them as pseudorandom functions. Okay, and we'll see why that's relevant later on. So here's a simple puzzle for you. Suppose f of xy is actually a secure PRF. Okay, so in other words, the adversary, once the key is fixed at random, the adversary cannot distinguish the resulting function from a random function from x to y. Now let's build another function g from this function f. So the function g is going to work as follows. Basically, if x is 0, the function g is going to output 0. And if x is not 0, it's simply going to output whatever f would output. Okay, so we kind of change the function f in just this one point, x equals 0. And my question to you, is this function g a secure PRF? So the answer, of course, is that the function g is not a PRF, because it's very easy to distinguish the function g from a random function. Simply query the function g at the point x equals 0 and test if the response, I'll say response, is equal to 0. So we test whether the response is equal to 0. If the response is equal to 0, we say that, well, the challenger is emulating the function g. If the response is not equal to 0, we say the challenger is emulating a truly random function. And clearly, this will distinguish between an emulation of g and an emulation of a random function, and therefore g cannot possibly be a PRF. So what this shows you is that it's very easy to take a secure PRF and break it. All you have to do is change it at one point, and already it stops being a secure PRF. So we're going to see how to use secure PRFs in the next segment.